Hello, and welcome to the third TI Precision Labs lecture discussing isolated gate drivers. In this video, we'll take a look at the core parameters that can serve as a benchmark for isolated gate driver technology. We'll examine the datasheet definition of the parameters, discuss the mechanisms which determine these parameters for isolated and non-isolated drivers, and show how these parameters combine to impact system performance with an example. The four parameters this lecture will focus on are propagation delay, pulse duration distortion, part-to-part or channel-to-channel skew, and common mode transient immunity. In the previous lecture, these parameters were at the core of many emerging improvements to common applications for isolated gate drivers. Propagation delay is defined as the total duration between an input crossing either the rising or falling threshold and an output reaching 10% rising or 90% falling, depending on the intended behavior. For example, an output may correspond directly to an input. In this case, the propagation delay from low to high is given by the time between the input voltage crossing the rising threshold and the output voltage reaching 10% of maximum value. And the propagation delay from high to low is given by the time between the input voltage crossing the falling threshold and the output voltage reaching 90% of maximum value. If the output is inverted, the only change to the definition is that now propagation delay from low to high depends on the falling input threshold, and propagation delay from high to low depends on the rising input threshold. In order to eliminate any differences due to drive strength or supply voltage, propagation delay should be measured with minimal or no load, and at a consistent supply voltage for both input and output. Propagation delay is a function of the circuitry between the input and the output. Low-side drivers can achieve propagation delay less than 20 nanoseconds thanks to the simple circuitry required for their implementation. Half-bridge drivers introduce a slower high-voltage level shifter, as well as some deglitching and filtering circuitry to avoid noise triggering the outputs. Inevitably, this adds to the total propagation delay, and more than 100 nanoseconds of delay is common. The difference in delay between low side and high side is great enough that a separate delay block must be introduced to the low side. Opto-isolators convert the gate drive signals to an optical signal with an LED, and the signal is detected by a photosensitive circuit such as a phototransistor or photodiode. LEDs, driven properly and with minimal additional parasitics, can switch on and off in tens of nanoseconds or less. With proper optimization of internal parasitics, transimpedance amplifier characteristics, LED drive strength, and many other design values, opto-isolators can achieve propagation delay similar to capacitive or transformer isolators, for a cost. More commonly, these design values are relaxed to allow acceptable propagation delay in the low hundreds of nanoseconds at a more competitive price. Capacitive and transformer isolators encode their binary output states on a high-frequency carrier, which can have a period of a few nanoseconds or less. Carrier demodulation may likewise take only a few nanoseconds, though in most cases the overall delay is longer because of internal logic delays and deglitching filters. Not all manufacturers implement their isolation modem the same way, even if they use similar technology. In other words, propagation delay is not set by an isolation medium, but by a technology using that medium with specific constraints. Every gate driver will see some variation in propagation delay due to process tolerances, changes in supply voltage, and changes over junction temperature. Careful design removes much of the effect of process tolerances. In an application environment, operating temperature usually remains consistent, and many parts also include internal regulators to maintain stable operating points. Temperature changes usually have the greatest impact on drift and propagation delay. Isolated drivers are not meaningfully affected by the application of high voltage across the isolation barrier, since the isolating element does not see a significant change in physical properties, and therefore the high-frequency transmission characteristics are not disturbed. Compare this to applying high voltage to the high side channel of a non-isolated half-bridge driver, which can impact the propagation delay by affecting the level-shifting transistor capacitance. To measure typical propagation delay, an oscilloscope probe with a low inductance ground sheath should be placed at the input pin and the output pin. The probes should be compensated beforehand, and both the probes and the oscilloscope should have sufficient bandwidth to measure the rising and falling edges of both the input and the output. For maximum accuracy, the approximate rising and falling thresholds should be located with an adjustable voltage source beforehand by increasing and decreasing the input voltage in small increments until transition is observed. Keep in mind that these thresholds will change with changes to supply voltage and temperature. Adequate bypassing capacitors must be present to ensure consistent internal supply voltage. Pulse duration distortion, or pulse width distortion in many datasheets, is defined by measuring the propagation delay from both low to high and high to low, and calculating the absolute difference between them. Because this parameter is defined by absolute difference, a positive value could be interpreted as either the maximum duration added to a pulse, or the maximum duration truncated from a pulse. Some manufacturers also specify this parameter without an absolute difference to distinguish between pulse extension and pulse truncation. Be sure to carefully examine component datasheets to confirm which definition is used. Pulse duration distortion in gate drivers depends heavily on design trade-offs and the isolation medium. The D-glitch filter has a measurable impact, since it is designed to reject pulses shorter than a minimum cutoff value. But since the impact is limited to duty cycle extremes, D-glitch filter distortion is not usually included in the pulse duration distortion value in the datasheet. Lower-cost opto-isolators can suffer from poor pulse duration distortion because the turn-on and turn-off times of the LED and the photodetector are not always symmetric, more so over temperature. Opto-isolators' pulse duration distortion ranges from hundreds of nanoseconds to tens of nanoseconds. Capacitive and transformer isolators experience pulse duration distortion because of the variation in oscillator timing accuracy, the transmission line characteristics of the isolating component, and the detection scheme on the receiver. Collectively, each may be responsible for a few nanoseconds. Pulse duration distortion in capacitive and transformer isolators is usually in the low tens of nanoseconds, occasionally less. To measure pulse duration distortion, the same test setup as propagation delay is reproduced, and data is collected for many pulses across duty cycle until pulse durations become comparable to D-glitch filter cutoffs. For drivers with programmable dead time, the feature must be bypassed. Statistical collection and persisting capture data are both helpful ways to observe the pulse duration distortion. Part-to-part or channel-to-channel timing skew, hereafter just timing skew, is defined by measuring the propagation delay for the same action taken by two parts or two channels, and finding the absolute difference between the two measurements. This measurement goes by many different names depending on manufacturer conventions, with names such as delay matching or difference between parts. Some parts may not print values for part-to-part timing skew. In these cases, the upper bound of skew is always the maximum guaranteed propagation delay, since the propagation delay maximum is the worst-case deviation from an ideal driver with no propagation delay. Generally, drivers with the same temperature, supply voltage, and lot code will have minimal timing skew. Consequently, any change in process, voltage, and temperature can increase timing skew. Drivers from different lots and different date codes will have slightly different characteristics. Even drivers from the same lot will have a spread of parameters due to their position on the wafer during construction. This is rarely an issue with channel-to-channel timing skew, since receivers are chosen from the same lot and are usually picked in pairs with minimal distance between the wafer positions. Differences in output voltage between the drivers can affect skew through propagation delay changes, though to some extent, on-chip regulators can be used to limit the effect of lower voltage logic elements. But the majority of skew arises from temperature variations between drivers or channels. Even for otherwise identical drivers, power consumption and thermal effects from layout and airflow may be completely different. For applications where timing skew is critical, efforts should be made to match driver temperatures, supply voltages, and lot codes. The test conditions for timing skew can vary considerably from conditions in the application environment. To measure timing skew, an oscilloscope probe with a low inductance ground sheath should be placed at the input pin and the output pin of both parts or channels to be measured. All other conditions, including length of input path, should be equalized for a datasheet measurement, though for production testing, the conditions should be matched to the worst case difference in the application environment. Rising edges should only be compared to rising edges, and falling edges should only be compared to falling edges. All only for parts with the same part number, or channels in the same part. Again, statistical collection and persisting capture data can help to find the worst case values. Common mode transient immunity, CMTI for short, is defined by the minimum required slew rate for a transient across the isolation barrier to corrupt the driver output state. At high slew rates, transients capacitively couple across the isolation barrier and inject currents into control circuits, causing the output state to become corrupted temporarily. In applications, this transient is commonly caused by high dVdt on the switch node, and can sometimes be caused by an avalanche breakdown from a transistor. Sometimes CMTI is separated into static and dynamic CMTI. Static CMTI allows inputs to be directly connected to reference planes, making it much harder for transients to generate an erroneous signal in the internal circuitry. Dynamic CMTI typically uses a microcontroller or other source with higher impedance to drive the inputs, which makes it easier for injected transient currents to affect the output state. The output will return to the expected state once the transient condition clears, and current injection to the control circuitry stops. Optoisolators have internal shielding that route transients away from critical internal circuitry, but this shielding creates capacitances that can inject common mode currents into the driving LED. Most of the challenges in minimizing these capacitances are mechanical, and well-designed packages are required to reach acceptable CMTI levels. Transformer isolators are primarily impacted by the parasitic capacitance between the transformer primary and secondary, though designers can adjust coil distance and placement to adjust the parasitic values. Capacitive isolators unavoidably couple the transient directly through the communication medium, and must be carefully designed to mitigate this problem. Designers use internal die area to strategically place shielding layers and bypass capacitances, steering transients away from critical signals as much as possible. Since these structures are constructed on die, their effectiveness and the driver CMTI rating are affected by process, voltage, and temperature variations. Measurement of common mode transient immunity can be complicated. First, an adjustable transient generator must be designed or selected. Examples include the switch node of a switching converter, a transistor-based Marx generator, or some other electrical fast transient generator. Second, the transient must be measured. Since bandwidth and rise time are inversely correlated, fast probes and a high-speed oscilloscope are required to measure fast transients. The probe voltage rating must also be considered for higher voltages. Finally, the output state must be monitored for changes. The CMTI test should be designed so that the driver output grounding point is always tied to the same ground as the oscilloscope. Floating the driver ground apart from the oscilloscope ground requires using a differential probe or an isolated probe, but the poor common mode rejection of fast high voltage transients leaves most differential probes with noise larger than the desired signal, and isolated probes with the required high common mode transient immunity are very expensive. Here is an example that integrates the lecture topics using a silicon carbide MOSFET half-bridge. Suppose that for our combination of drain current, load inductance, and gate drive characteristics, we can expect turn-on and turn-off times of no less than 25 nanoseconds and no greater than 35 nanoseconds. We can also expect the rise and fall times to be 10 nanoseconds and 8 nanoseconds respectively. These parameters are relatively stable over temperature, and the 800-volt bus voltage is unchanging. What would be the minimum required dead time for this system over operating temperature if we consider using two TI ISO 5852S drivers with these characteristics, two transformer drivers with these characteristics, or two optoisolators with these characteristics? These examples are chosen from comparably priced components. Let's assume the drive strength of each driver is sufficient to meet the 35 nanosecond turn-on and turn-off time. In all cases, the propagation delay from low to high and from high to low is closely matched. These equations give the minimum conditions to prevent shoot-through in the bridge, for skew calculations, and for propagation delay calculations. For the capacitive driver ISO 5852S, the minimum required dead time based on part-to-part skew is 40 nanoseconds, though normally this is extended by a small amount to add some margin for error. Using propagation delay, the minimum dead time almost triples to 110 nanoseconds plus margin, since minimum propagation delay is not known and can never be less than 0 nanoseconds. If you find a driver with less than 0 propagation delay, please let us know. For the transformer driver, no part-to-part skew figure is given. Based on the distortion provided in the datasheet, it can be inferred that two parts at the same voltage and across temperature will never see a skew greater than 60 nanoseconds, and so the theoretical minimum required dead time is 70 nanoseconds plus margin. Using propagation delay, we can determine the absolute delay difference across temperature to be 90 nanoseconds, and the minimum required dead time becomes 100 nanoseconds plus margin. For the optoisolator, both part-to-part skew and propagation delay are provided across temperature. Minimum required dead time using part-to-part skew is 360 nanoseconds plus margin, and using propagation delay this estimate increases to 410 nanoseconds plus margin. Optoisolators tend to be slower than most modern isolated gate drivers, and for silicon carbide systems, this is a strong disadvantage. Optoisolators with enhanced timing characteristics do exist, but they are pricey. What about CMTI? The rise and fall times of 10 nanoseconds and 8 nanoseconds respectively, combined with the 800-volt bus voltage, suggest a worst-case slew rate of 100 volts per nanosecond. Note that this is within the ratings of the capacitive isolated gate driver, but it exceeds the maximum of the transformer driver and flies well above the guaranteed minimum of the optoisolator. In order to use the transformer driver or the optoisolator with confidence, an external gate resistor must reduce the rise and fall time, bringing the slew rate within the component limitations. Consequently, the turn-on and turn-off time assumptions may be violated, requiring the propagation delay calculations to be recomputed. In the remaining lecture, we will briefly discuss common challenges faced by gate driver application circuits, and some of the features designed to solve these problems. That concludes this video. Thank you for watching. Please try the quiz to check your understanding of this video's content.